Okay, good. So I'm going to talk about the phase behavior and topological defects in a system of self-propelled particles in 2 dimensions. This is an ongoing work that I started during my PhD at the University of Bari, and then at that time continuing here in my postdoc here in Lausanne. So this is what I'm gonna talk about. I will first give a brief overview about the theory of melting in 2D, which is a bit the background of our work. Then I will introduce the model of self-propelled particles, and then I'll move to talk about the focus of this project, which concerns topological defects, and as you will see later, it includes both point-like defects and extended defects. So, starting with melting. So, as you might know, melting of a system of disks, of art disks, let's say in 2 dimensions, proceeds in 2 steps. From the solid to the liquid. The scenario of melting results from the so-called Kosterlitz-Tauler Nelson theory, after the name of the scientist who first addressed this problem. And okay, the reason why we have this this double-step scenario is because actually we have 2 types of order in our system. So the first type of order that we have is the standard translational order concerning the position of the disks in the system, but also we have another kind of order concerning the orientation of the bonds between neighbor particles, as you can see in this sketch here. So as you all know, in a system of in a 2-dimensional system of disks, the ordered phase, the structure of the ordered phase is the one where all the disks are placed over, let's say, the vertices of a triangular lattice. So in this case, we will talk about concerning this bond orientational order. We will talk about hexatic order. So. Okay, as I was saying, the route of the melting from the solid to the liquid goes through this intermediate hexatic phase. And according to the Kosterlitz-Tauler Nelson theory, the first phase transition from the solid to the hexatic, where the solid phase is the one, is the one with the with translational order, while the hexatic phase, as I told you, is the one with the orientational order. So the first phase transition from the solid to the hexatic is driven by. Okay, let me just describe you first this picture. So in these pictures here, the gray disks are the ones with the right number of neighbors, which is 6, while the red particles have 5 neighbors, and the blue particles have 7 neighbors. So, so let's say isolated particles with 5 or 7 neighbors are the isolated disclinations. I mean, it can be 5-fold or 7-fold defects, giving rise to different types of free disclinations. Red-blue pairs, which means 5-fold, 7-fold pairs, are free dislocations. So the solid here can accommodate dislocation pairs. Then the solid to the hexatic phase transition is driven by the unbinding, a process of unbinding of these dislocation pairs into free dislocations. And then the second phase transition from the hexatic to the liquid is instead mediated by the unbinding of free dislocations into free disclinations. Okay, although this theory is a long-standing problem statistical physics, there are still some unanswered questions, let's say. First of all, the nature of the liquid hexatic, or hexatic liquid melting, is not universal, but it depends on the interactions between particles. In particular, it can be, I mean, it has been shown that moving from the hard disk's limit, where the hexatic liquid phase transition is a first-order phase transition, we have a crossover between a first-order phase transition and a continuous phase transition as we move from the hard disk limit towards systems where the interaction between particles is more soft. Also, concerning this process of unbinding of defects, there are not to date like clear observation of these two processes of unbinding of defects related to these two phase transitions. So, I mean, the idea of the project, I mean, the starting idea of the project is to look a bit, is to give some further observation of these two unbinding process related to this particular double-step melting transition. Okay, before talking about defects, let me say that I mean, other than exploring more in detail the properties of a standard hard disks model, we are very much interested also in the study of this melting phase transition, but in system of self-propelled disks. So self-propelled disks are basically a self-propelled disk model is a model where particles are supplied by an amount of energy, and they can transform in this energy into directed motion. So, but the problem is that, I mean, the thing is that this injection of energy into the system drives the system out of thermal equilibrium. So we are talking about out of equilibrium, an out of equilibrium problem. The model we use to realize this self-propelled motion is a standard, let's say, model of Brownian particles, where all the particles experience an extra force, a self-propulsion force of constant magnitude and direction, and I mean the direction of this self-propulsion diffuses in time with a given diffusion coefficient. And in our case, the diffusion coefficient is related to the temperature of the bath. So in the end, the only way we can change, we can tune the strength, I mean the strength of the self-propulsion of these disks is to increase or decrease the magnitude of the active force. I mean, giving the temperature of the bath is constant. That is more or less always the case for our studies. So the way we define the parameter that controls the strength of the self-propulsion is the definition of this so-called Pasquale number, which is proportional basically to the strength of the active force. Okay, let me show you this two videos that illustrates a bit the behavior of these particles. So basically, compared to the standard Brownian motion, our self-propelled particles perform a so-called persistent random walk, which means that they are able to keep moving in the same direction for a given extent of time. And okay, the persistency of this motion can be tuned by tuning the strength, as I told you, of the active force, or if you want, by changing the Pasquale number. Okay, the phase diagram of this model is already known. We already established the main features of the phase diagram of this model, and there are a couple of features that I want to mention before going on. So the first time, the first thing is that for a large extent of values of activity, we always observe this double step melting. So this means that even if the system is active, at high enough density, we will observe a solid phase, and then we will observe a melting into the hexatic and a second melting from the hexatic to the liquid. The second main feature that I want to show you is that actually the nature of hexatic liquid phase transition changes as soon as we turn on activity in our system. And as you can see here, while the hexatic liquid phase transitions, as I mentioned before, for the passive system, for the classical hard disk model, is a first order phase transition with a coexistence region. As soon as we turn on a bit activity, we observe again a crossover between the first order phase transition and the second order, a continuous phase transition. So, okay, just please bear in mind that for the next part of the talk, I will always refer to this phase diagram when I will talk about solid hexatic and hexatic liquid phase transition. Because, the way we proceed, so we first establish for example, the location and the characteristics of these two phase transition by looking at by studying the correlation functions of the two local order parameters, and then we build from the properties of this phase diagram all the studies about defects. So let me say the purpose of our work is twofold, because we are interested in, let's say, clarify the microscopic mechanism, which involves topological defects, as in the Kosteles-Thouless theory, the microscopic mechanism that mediates the melting, both for the passive and the active system. So, having in mind a picture of the Alpern-Nelson picture of melting, we started looking at the topological defects which are expected to play some role in the melting. So we counted the number of free disclinations and free dislocations in our system, and as you can see here, and we did it both for the passive and the active system. And as you can see here, we always observe for the Peclet 0 case and all the values of Peclet we explored that free dislocations proliferate across the solid to hexatic phase transition, while free disclination, say, are excited when we move from the hexatic to the liquid. In particular, they just proliferate at the hexatic liquid phase transition in the active case where we have continuous phase transition, and we start seeing free disclination at the beginning of the coexistence region at Peclet 0, where we have a first order phase transition. Okay, so other than simply counting the defects, we can do even more. We can look at the way the number of defects, the number density of defects goes to 0 at the transition. So from the Kosteles-Thouless theory, we have a theoretical prediction of the form of the critical divergence of the correlation length for the two different phase transition. And from this form of the critical divergence of the correlation length, and from a simple scaling argument, we can, let's say, we can give a prediction of the way our number of defects should go to 0 at the phase transition. So we basically compare our measure of the number of defects with these predictions coming from the theory, and we did it for both from the solid hexatic phase transition using the expected exponent coming from the theory, which is 0.37, and from the hexatic liquid phase transition where the exponent is 0.5, and we found a general good, strong agreement of our data with the behavior predicted by the theory. One thing to be noted is that, okay, if we apply this such form of the decaying for the defects, we just, I mean, this brings another independent estimate of the critical point of the transition, because as you can see here, you can use this phi c in the form of the decay of the number of defects as a fitting parameter. So you have a second independent estimates of the critical point. And the thing we observe is that while for the solid hexatic phase transition, this the second estimate is strongly in agreement with our previous estimate, this is not the case anymore this is not the case for the hexatic liquid phase transition, because as you can see here, the estimates of the phi c that comes from the fit of this predicted behavior departs a bit from the one that we expected from our previous measurements. Okay, this suggested us to look a bit closer to the behavior of disclinations. And actually, as you can see from this picture, while we do observe unbinding of free dislocations, and we do observe free dislocations in the sense they are basically alone in the nearby. Okay, here these locations are highlighted with the blue circle. We never observe true isolated free disclinations, in the sense that they are always bonded either together or with other, let's say, extended structures of defects. This is quantitatively confirmed by the study of defects radial distribution function. So as you can see here, while for dislocation radial distribution function, the probability of finding neighbors, let's say, the probability of finding, I mean, the pair, the distance probability between pairs of dislocation is more broader, and it means that there is a significant probability of finding two dislocations at very farther apart each other. The radial distribution functions for disclination radial distribution functions, the probability is really concentrated around a value of r equal to 2 times the diameter of the particle. This is also confirmed by these plots here, which represents let's say the average numbers of neighboring defects for a given dislocation and disclination. So as you can see here, the number of neighboring defects for disclinations grows much faster, which means that I mean, it's on average, we always find some defective particle nearby free disclinations. And okay, in a way, so in a way, this contradicts a bit the prediction of the Kostelis-Taules theory concerning hexatic liquid phase transition, because we should observe in correspondence of this transition a true unbinding of these kind of defects, while we observe also bonded bonded disclinations. So the natural question that arises is that there is any other mechanism involving defects associated to the liquid hexatic phase transition. Well, the answer to this question is yes, and this mechanism is associated to the presence of these extended clusters of defects. So what we basically did is to map the problem of defects into a percolation problem. In particular, we mapped this problem into a side percolation problem on a square lattice, where the occupied sides are the sides that are actually occupied by defects. And what we found from this mapping, let's say, is that actually we do observe percolation of defective clusters close to the hexatic liquid phase transition. And the interesting thing is that we always observe critical percolation together with hexatic liquid phase transition, both in the passive case and in the passive case, we observe the same percolation behavior both for the hard disk model, where we have, I remind you, we have a first order hexatic liquid phase transition, and also for the soft disks, where we have a continuous hexatic liquid phase transition. Then also in the active case, for all the values of the parameters of the activity of the Peclet number that we explored, we always found that in correspondence of the hexatic liquid phase transition, there is this percolation of defective clusters. So, I mean, let me say this. This tells us that actually a percolation critical point is quite general phenomenon associated to the hexatic liquid phase transition, because I mean it is always there regardless let's say the microscopic behavior of the microscopic characteristics of the system. So we could I mean we can use this finding and I mean the percolation critical point as a way to explore a bit more the properties of the defective clusters. And for example, here, as you can see from the power law of the critical decaying of the cluster size distribution, which is related, according to the percolation theory, to the fractal dimension of the percolating clusters, we can confirm somehow the idea that, for example, the fractal dimension of I mean, the defective clusters get more string-like by increasing the activity, for example. So, just to summarize a bit the results of this work. So first of all, we found that dislocation unbinding is a general mechanism for the solid hexatic phase transition, not only for the passive system as predicted from the Kostelis-Taules theory, but also for the active system. So, I mean, it's truly related to this kind of phase transition. Instead, for the disclinations, we don't observe any unbinding process, like the one predicted by the theory, and yeah, we don't observe any unbinding process, but for the hexatic liquid phase transition, we do observe a percolation critical point, which is strongly related to the hexatic liquid phase transition, and can be with all generality associated to this kind of hexatic liquid melting. So with this, I concluded, and I thank you for the attention. If you have any questions.
Thank you very much, Lino. So, questions or comments? We can open the discussion if there are any questions. Perhaps I can start myself with a question. I mean, it seems that most of your results are valid both for passive and active system. Is there something where, I mean, they are, let's say, crucially different?
Well, yes, of course it is, because I mean, I didn't have the time to show you, but of course, compared to the passive case, the active systems, I mean, the active particle system shows a lot of, let's say, interesting phenomena, which are not present in the passive case. Just to mention, I have few slides. We have this phenomenon that is motility-induced phase separation, which is primary of active system only. And also here, I mean, the study of defects, I won't go into the detail, but the study of defects here is really interesting. It gives a lot of interesting insights into this kind of phenomena, which exists only for the active system.
Okay, thank you. Other questions or comments?
Can you hear me?
Yes, please.
Yes.
Hi, Pasquale.
Hi.
First of all, I would like to say that I thank you for the nice seminar that has been clear. I just would like to be sure that regarding the liquid hexatic or the hexatic solid transition in homogeneous system, basically the difference between active and passive is the same. Since to answer the question of Rosario, you mentioned the motility-induced phase separation. So my question was, is it really very similar, the mechanism between the liquid hexatic transition and the hexatic solid transition from active and passive cases, or not?
Well, actually, yes, that's correct.
So is
I go back to some slide. As you can see here, if you look at the behavior of defects, I mean, we observe a similar behavior, a similar unbinding of free dislocations, etc., for all the cases. I mean, for Pasquale 0 for the passive case and for the active cases. So yes, interestingly, this phenomenon is really strongly related to this phase transition, even in the active case. And the same is for disclinations.
But it seems that for the dislocations, if I interpret it in the correct way, the graph on the left, you see that the activity, so an high Pasquale number decreases the number of dislocation, right? Near the critical point, of course, maybe this is not.
You mean this? I mean, you are talking about the slopes of these curves. Well, yes, you can say that, but in the end, I mean, you have to be careful comparing these cases because, well, I didn't go into the details, but here, for example, the extension of the hexatic region is different while you increase the activity. So you have to, I mean, if you want to study, I mean, and to let's say interpreting the slope of these curves, you have to normalize this plot with respect to the, let's say, at least to the width of the hexatic region that changes. So I mean, I agree. It looks like the slope of these curves is changing, and activity is somehow suppressing the proliferation of free dislocations. But I mean, I will not be so sure about the generality of this property.
Okay, thank you.
Other questions or comments? So if not, I think we can thank Simona and Lino for the presentations and close the seminar here. Thank you very much for.
Thank you.
And see you next month for the next 2 seminars.
Okay. Thank you. Bye.
Bye bye.
Saluti a tutti.
Ciao a tutti.
Ciao.
Ciao a tutti.
Thank you to everybody. Ciao.
Oh, bye bye.
Ciao. Ciao Rosario. Ciao a tutti.
Ciao.
Ciao
Ciao
Eugenio.
Federico.
Ciao.
Ciao Eugenio.
Ciao. Bene. Ciao a tutti.